There is a sentence sitting somewhere right now that cannot be true and cannot be false, not because it is vague or poorly written, but because the logic of the sentence itself makes both options impossible. It is not a trick. It is not a riddle with a clever answer waiting at the end. It is a genuine crack in the foundation of formal reasoning, and it has troubled mathematicians and philosophers for over 2,000 years. Logic is the tool we use to distinguish truth from falsehood. It is the backbone of mathematics, of computer science, of law, of science itself. We assume that any statement, at minimum, must be one or the other, true or false. But a small class of sentences breaks that assumption completely. And understanding why they break, it tells us something deep and uncomfortable about the limits of human reasoning. The first of these cracks in logic is something called the liar paradox. It is perhaps the oldest known paradox, traced back to the ancient Greek philosopher Epimenides, and later refined into its sharpest form by thinkers in medieval Europe. The sentence at the heart of it is deceptively simple. Write these words on a piece of paper. This statement is false. Now try to evaluate it. Suppose the statement is true. If it is true, then what it says must accurately describe reality, and what it says is that the statement is false. So if it is true, it must also be false. That is a contradiction. Now suppose the statement is false. If it is false, then what it says is not accurate. What it says is that the statement is false. So if it is false, then it is not false, meaning it must be true. Another contradiction. There is no exit from this loop. The statement cannot be true without being false, and cannot be false without being true. It is trapped in permanent self-contradiction. Unlike a math problem with a tricky solution, or a riddle with a surprising answer, the liar paradox has no resolution that preserves ordinary logic intact. It simply refuses to fit. What makes this more than a curiosity is what it implies for formal systems. In the early 20th century, mathematicians tried to build mathematics on an absolutely solid logical foundation. The goal was to prove that mathematics was consistent, meaning free of contradictions, and complete, meaning every true statement could eventually be proved. The liar paradox played a central role in showing why this goal could not be achieved. The logician Bertrand Russell, working in the early 1900s, recognized that the liar paradox was a symptom of a deeper problem: self-reference. When a statement refers to itself, the normal rules of evaluation break down. He tried to solve this by building a hierarchy of types, where statements could only refer to objects at lower levels, not to themselves. This helped contain the damage but did not eliminate the underlying tension. Then in 1931, the mathematician Kurt Gödel used the structure of the liar paradox to prove something that stunned the mathematical world. He showed that in any sufficiently powerful formal system, there will always be true statements that cannot be proved within that system. This result, known as Gödel's Incompleteness theorem, demonstrated that the dream of a complete and consistent foundation for all of mathematics was logically impossible. The liar paradox was not just a quirky sentence. It was a key that unlocked one of the deepest truths about the nature of formal reasoning itself. Not all paradoxes attack the structure of logic directly. Some attack our intuitions about prediction, surprise, and knowledge. And few do this more elegantly than a puzzle known as the unexpected hanging paradox. Imagine a judge addressing a prisoner on a Friday afternoon. The judge says clearly and deliberately, "You will be executed at noon on one of the 5 weekdays of next week, Monday through Friday." Furthermore, the execution will be a surprise. On the morning it happens, you will not be able to know with certainty which day it is until the executioner arrives at your cell. The prisoner is led back to his cell, and he begins to think carefully. He reasons through each possibility, starting from the end of the week and working backward. Friday is the last possible day. If he reaches Thursday night still alive, there is only one day left, and he would know with certainty that Friday is the day. But then it would not be a surprise, so Friday is eliminated. Now with Friday gone, Thursday becomes the last possible day. If he survives to Wednesday night, and Friday is already ruled out, then Thursday must be the day. But again, he would know, so Thursday is eliminated too. He applies the same reasoning to Wednesday, then Tuesday, then Monday. Each day eliminates itself using the same logic. By the time he finishes, he has convinced himself that the execution cannot happen at all, because no matter which day it falls on, he would be able to predict it the night before, and it would therefore not be a surprise. Feeling confident in his deduction, he relaxes. He sleeps well. He even begins to enjoy the strange freedom of believing himself safe. Then on Wednesday morning, the executioner arrives. The prisoner is completely stunned. He had no idea it would be Wednesday. The judge's promise was kept perfectly. So what went wrong with the prisoner's reasoning? The paradox has generated substantial debate among philosophers and logicians, and there is no single universally agreed upon resolution. But the central problem seems to lie in how the prisoner uses his own reasoning. His chain of deductions assumes that each conclusion is known and stable, but the knowledge he relies on is not stable. It depends on assumptions about what he will or will not know in the future, and those assumptions collapse when examined carefully. More specifically, the prisoner's logic works only if we grant that each eliminated day is truly and permanently ruled out. But the judge's statement is not a logical theorem. It is a claim about the future, and predictions about surprises are notoriously slippery. The prisoner treats the judge's words as if they form a closed logical system he can fully analyze from inside. But he cannot. His conclusion that no execution can happen is itself based on faulty premises about what constitutes proof and what constitutes surprise. What the unexpected hanging paradox reveals is a subtle but important gap between formal logical reasoning and reasoning about knowledge, belief, and future events. It shows that the rules of classical deduction do not transfer cleanly into situations involving time, expectation, and self-referential claims about what we will know. A different kind of paradox concerns not time or prediction, but the very idea of consistent rules, and it is one of the most famous logical puzzles in history. It begins with a small town and a single barber. In this imaginary town, there is exactly one barber. The barber follows one simple rule. He shaves all and only those men in town who do not shave themselves. If a man shaves himself, the barber will not touch him. If a man does not shave himself, the barber will shave him. The rule sounds reasonable at first glance. It divides the male population neatly into two categories, self-shavers and non-self-shavers. But then comes the question, who shaves the barber? Consider the first option. Suppose the barber shaves himself. According to the rule, the barber only shaves men who do not shave themselves. But if the barber shaves himself, he is shaving someone who does shave himself. That violates the rule. Consider the second option. Suppose the barber does not shave himself. According to the rule, the barber must shave all men who do not shave themselves. Since the barber does not shave himself, he falls into that category, so he must shave himself. But that brings us back to the first option, which also violated the rule. There is no way out. If he shaves himself, he shouldn't. If he doesn't, he must. The rule makes the barber's existence logically impossible. This is the Barber Paradox, formulated by Bertrand Russell in the early 1900s as an intuitive way to illustrate a more abstract problem in set theory. In mathematics, a set is a collection of objects. Russell wondered, can there be a set of all sets that do not contain themselves? He found that such a set leads to the exact same contradiction as the barber. If it contains itself, it shouldn't. If it doesn't contain itself, it must. This became known as Russell's paradox, and it showed that the naive definition of a set, as simply any collection of objects satisfying a rule, was fatally flawed. Some collections create logical contradictions, and the mathematical tools of the time could not handle them. The discovery sent shockwaves through the foundations of mathematics and motivated decades of careful work to rebuild the theory of sets on safer ground. Modern set theories resolve this by placing restrictions on what kinds of sets can be formed. You cannot simply collect together any objects you like and call it a set without obeying careful constraints. The barber, in this framework, simply does not and cannot exist. The paradox is not resolved by finding an answer. It is resolved by recognizing that the question describes something impossible. From the relatively contained world of set theory, another paradox takes us to the banks of a river, to a crocodile with an unusual moral framework. The Crocodile Paradox is ancient in origin, known to scholars in Greece and later in medieval Europe, and it shares deep structural similarities with the Liar Paradox. A crocodile seizes a child from the riverbank. The desperate parent pleads for the child's return. The crocodile, operating under its own unusual code of logic, offers a deal. It will return the child if and only if the parent correctly predicts what the crocodile will do next. The parent thinks carefully and makes a prediction. You will not return my child. Now the crocodile is trapped. If the crocodile was not going to return the child, then the parent's prediction is correct, and according to the deal, the crocodile must return the child. But if it returns the child, then the prediction, which said it would not return the child, turns out to be wrong. And if the prediction is wrong, the crocodile is not required to return the child. But then the prediction becomes right again. and so on, indefinitely. The structure here mirrors the liar paradox exactly. The prediction and the outcome are each defined in terms of the other, creating a self-referential loop that logic cannot escape. No action the crocodile takes is consistent with the terms of the deal. The Crocodile Paradox is not merely a puzzle about reptiles and riversides. It has practical implications for systems built on conditional agreements. In contract law, agreements sometimes contain clauses that reference each other in circular ways. In artificial intelligence, systems designed to satisfy certain conditions can encounter situations where the conditions cannot all be satisfied simultaneously without contradiction. The paradox raises a deep design question. How do you build a rule-following system that can survive a contradiction without breaking? In most real-world legal systems, paradoxical contracts are simply declared void. The courts refuse to enforce an agreement whose terms cannot be coherently evaluated. But in systems that must operate automatically, without a judge to step in and declare an impasse, these situations become genuinely dangerous. The Crocodile Paradox, in this sense, is not just an ancient riddle. It is a preview of challenges that computer scientists and engineers face when building systems that must reason about their own rules. Moving from the abstract world of self-referential logic to the physical world of motion and space, we encounter one of the oldest paradoxes ever formulated. It dates back to ancient Greece, to a philosopher named Zeno of Elea who lived around 490 years before the Common Era. Zeno constructed several arguments designed to show that motion is impossible, or at least that our common sense understanding of it is deeply confused. The most famous of these is the paradox of Achilles and the tortoise. Imagine a race between the legendary warrior Achilles and a tortoise. Because Achilles is far faster, the tortoise is given a head start of 10 meters. The race begins. Achilles runs to the spot where the tortoise started. But while Achilles was covering those 10 meters, the tortoise has moved ahead, perhaps only 1 meter, but it has moved. Now Achilles runs to that new position, but again, the tortoise has advanced a little further. Achilles closes the gap, and again, the tortoise is slightly ahead. Zeno's argument is that this process never ends. Every time Achilles reaches where the tortoise was, the tortoise has moved on. The gaps become smaller and smaller, but there are infinitely many of them. And Zeno argued that to traverse infinitely many steps, no matter how small, must take infinite time. Therefore, Achilles can never overtake the tortoise. Of course, in any real race, Achilles overtakes the tortoise easily. We can observe this. We can time it. The conclusion of Zeno's argument is clearly wrong in practice, but identifying the precise logical error took over 2,000 years. The resolution came through the development of mathematics powerful enough to handle infinite series. When you add up the infinite sequence of time intervals it takes for Achilles to complete each step, something remarkable happens. Even though there are infinitely many steps, the total time they require is finite. This is because the steps themselves shrink rapidly enough that their sum converges to a definite number. As a simple illustration, the series 1/2 plus 1/4 plus 1/8 plus 1/16 continuing forever adds up to exactly 1. There are infinitely many terms, but the total is finite. Achilles takes infinitely many steps in the mathematical description of his motion, but those steps collectively require only a finite amount of time. He catches the tortoise at a specific, calculable moment. This understanding was formalized through the development of calculus in the 17th century by Isaac Newton and Gottfried Wilhelm Leibniz. The mathematics of limits and infinite series gave us the tools to handle what Zeno's intuition could not. An infinite sequence of steps does not necessarily require infinite time if the steps shrink fast enough. But even with this mathematical resolution, Zeno's paradox leaves behind genuine philosophical questions. The resolution tells us how to calculate where and when Achilles catches the tortoise. It does not tell us what motion actually is at the deepest level. Is space infinitely divisible, as Zeno assumed? Or does space come in discrete, indivisible chunks at the smallest scales? Modern physics offers reasons to wonder about both possibilities. At the scale of the Planck length, approximately 1.6 times 10 to the negative 35 meters, our current theories of physics begin to break down. Whether space itself is continuous or granular at that scale remains an open question. Zeno's paradox, then, is not just resolved and filed away. It continues to echo through physics and philosophy, raising questions about the structure of space and time that remain active areas of research today. From the infinite divisibility of space, we turn to a paradox that bends time itself into an impossible loop. It is called the Grandfather Paradox, and it stands as the central puzzle of theoretical time travel. Suppose you build a machine that can carry you backward through time. You decide to travel back to a period before your grandparents met. Perhaps by accident, perhaps by intention, your actions prevent them from ever encountering each other. They never fall in love. They never marry. Your parent is never born, and therefore, you are never born. But here lies the paradox. If you were never born, you could not have built a time machine. You could not have traveled back in time. You could not have prevented your grandparents from meeting. So your grandparents do meet. Your parent is born, you are born, you build the machine, you travel back, and you prevent the meeting again. The loop has no consistent resolution. This is not a problem of technology or engineering. It is a problem of logic. The sequence of events requires that your existence both causes and prevents itself. No timeline can accommodate both requirements simultaneously. Physicists and philosophers have proposed various ways to think about this problem, and they divide broadly into a few categories. One approach is the idea that the timeline is self-consistent. Under this view, sometimes called the Novikov self-consistency principle after the Russian physicist Igor Novikov, any event that occurs in the past is part of a fixed, unchangeable history. If you travel back in time, your actions are already incorporated into the history that led to your birth. You cannot prevent your grandparents from meeting, because the historical record already shows that they did meet. Something will always intervene. A missed train, a wrong turn, a chance encounter that reassembles what you tried to separate. The universe, in this model, conspires to maintain consistency. Another approach is the many worlds interpretation, borrowed from quantum mechanics. Under this view, when you travel back in time and take an action that would create a paradox, the timeline does not loop back on itself. Instead, it branches. The action you take creates a new, separate timeline diverging from your original one. In that new timeline, your grandparents do not meet, and your counterpart in that timeline is never born. But in the original timeline, nothing changes. You still exist. You simply can no longer return home, because home belongs to a timeline that no longer connects to the one you have created. A third possibility, darker and more final, is that you simply succeed in erasing yourself. You travel back, prevent the meeting, and vanish from existence as a consequence. No loop, no paradox, just the termination of a causal chain. But this raises another question. If you vanished, who went back in time to create the chain of events that led to the meeting being prevented? Once again, the logic collapses. The Grandfather Paradox matters beyond science fiction. It is a serious constraint on the physics of time travel. General relativity, Einstein's theory of gravity and space-time, does allow for mathematical solutions that describe what are called closed time-like curves, paths through space-time that loop back on themselves, theoretically allowing travel to the past. But physicists debate vigorously whether such solutions can occur in reality, or whether the laws of physics contain some deeper principle that prevents them. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent the formation of closed time-like curves and thereby protect the consistency of history. The conjecture has not been proved, but it reflects a common intuition that a universe permitting time travel to the past would be one riddled with unresolvable contradictions. What all of these paradoxes share, despite their very different surfaces, is a common structure. They all arise at the boundary of what formal systems can handle. The liar paradox and the Barber paradox expose the limits of self-referential logic. The unexpected hanging paradox reveals the gap between abstract deductive reasoning and reasoning about knowledge and time. Zeno's paradox challenged our understanding of infinity and continuity, and was only resolved when mathematics developed new tools powerful enough to handle infinite series rigorously. The Grandfather Paradox tests whether the laws of physics are consistent with backward causation, and no one yet knows the answer. These are not failures of human intelligence, they are discoveries. Each paradox marks a point where our intuitions and our formal tools meet a genuine boundary. And at each boundary, the attempt to understand the paradox more deeply has led to new mathematics, new physics, new logic, and new ways of thinking. Russell's engagement with the Barber Paradox helped give birth to modern set theory. Gödel's engagement with the liar paradox produced the Incompleteness theorems, which transformed our understanding of mathematics and computation. The attempt to resolve Zeno's paradoxes contributed to the development of calculus. The Grandfather Paradox continues to drive serious research into the physics of space-time and the nature of causality. The paradoxes that feel most unresolvable are often the ones that mark the location of the next major advance in understanding. They are not signs that reasoning has broken down. They are signs that reasoning is approaching something real and important that it does not yet have the tools to handle. The history of human thought is in large part a history of confronting exactly these moments. A question arises that cannot be answered within the existing framework. The question refuses to go away, and eventually, someone builds a new framework in which the question can finally be addressed, even if the answer turns out to be that the question itself was slightly wrong. We do not know yet whether time travel to the past is possible. We do not know whether space is continuous or granular at the smallest scales. We do not know how to build artificial reasoning systems that can navigate genuine logical contradictions without breaking. These are open questions, and the paradoxes we have explored point directly toward them. What we do know is that every one of these puzzles, from the ancient paradoxes of Zeno and the liar, to the sharper formulations of Russell and Gödel, to the thought experiments about time machines and crocodiles, has told us something true and lasting about the structure of reality and the reach of the tools we use to understand it. The liar paradox cannot be resolved by being clever. It can only be addressed by changing the rules of the game, by building a logic that does not permit certain kinds of self-reference, or by accepting that some questions simply fall outside the domain of what formal systems can answer. Gödel showed that this is not a temporary limitation waiting to be overcome. It is a permanent feature of sufficiently powerful formal systems. There will always be truths they cannot reach. The unexpected hanging paradox cannot be dissolved by more careful reasoning within the prisoner's framework. It requires stepping back and questioning the framework itself, questioning what it means to know something about the future, and whether a judge's statement about surprise can ever be fully formalized. The Barber Paradox is resolved cleanly, but only by concluding that the barber does not exist. The rule that defined him was self-contradictory, and self-contradictory rules cannot describe real objects. The lesson generalizes. When a formal system produces a contradiction, something in the system's foundations must be revised. Zeno's paradoxes were resolved by the mathematics of limits and infinite series, but they left behind questions about the physical structure of space and time that remain active. And the grandfather paradox, if it is ever resolved, will require either a deeper theory of space-time than we currently possess, or a proof that certain mathematical structures in general relativity cannot arise in physical reality. In each case, the paradox is not the end of the story. It is the beginning. It marks the place where our current understanding reaches its edge, and where the next understanding must begin to grow. The questions these paradoxes raise are not going away. They will be answered, if they are answered, not by one clever person reasoning carefully, but by the slow accumulation of new mathematics, new experiments, new frameworks, and new ways of asking the questions themselves. The universe appears to be a place where logic is deep and powerful, but not unlimited, where infinity is real but subtle, where time may be more flexible than our daily experience suggests, and where the sentences we write, and the rules we construct, and the systems we design can always find the edges of what those systems can contain. That is what paradoxes are for, not to frustrate us, but to show us exactly where the edges are. To understand why paradoxes matter so deeply, it helps to understand what we mean by formal reasoning, and why human civilization has invested so much effort in building systems of logic that are as precise and reliable as possible. For most of human history, reasoning was something people did informally. Arguments were made in natural language, evidence was weighed by judges and councils and scholars, and the standard for what counted as a good argument was largely one of persuasion and coherence, rather than strict formal correctness. This worked reasonably well for everyday purposes, but it left open the possibility of subtle errors, hidden assumptions, and arguments that seemed valid but contained invisible flaws. The ancient Greeks were among the first to attempt something more ambitious, a system of reasoning so rigorous that its conclusions would be guaranteed correct by the structure of the argument itself, independent of any appeal to authority or intuition. Aristotle developed the first systematic theory of logic around 350 years before the Common Era. His syllogistic logic identified patterns of valid argument, forms that, if followed correctly, would always lead from true premises to true conclusions. This was a profound achievement, but Aristotle's logic was also limited. It could handle certain kinds of arguments cleanly, but it had no tools for dealing with infinity, with self-reference, or with reasoning about what we know and do not know. These limitations would remain largely unaddressed for 2,000 years. The next major leap came in the 17th century with the development of algebra and calculus. Mathematicians began to realize that symbols and equations could capture relationships between quantities in ways that natural language could not. A calculation in algebra is not subject to the ambiguities of interpretation that plague ordinary argument. If the symbols are defined correctly and the rules of manipulation are followed, the result is guaranteed. This inspired a dream. Could all of mathematics and eventually all of reasoning be reduced to symbolic manipulation? Could we build a language so precise that any question expressible in it could be resolved by following formal rules, without any need for intuition or judgment? Gottfried Wilhelm Leibniz, the 17th century mathematician who co-invented calculus alongside Newton, envisioned exactly this. He imagined what he called a characteristica universalis, a universal formal language in which all concepts could be expressed, and a calculus ratiocinator, a system of rules for manipulating expressions in that language. Any dispute, he thought, could then be resolved by saying, "Let us calculate." This vision remained a dream for 200 years. Then, in the mid-19th century, the British mathematician George Boole published a work called The Laws of Thought, in which he showed how logical reasoning could be expressed using algebra. Boole's algebra of logic was a remarkable achievement. It demonstrated that reasoning was not something mystical or intuitive, beyond the reach of mathematical treatment. It was a formal operation that could be captured symbolically and analyzed mathematically. Boole's work inspired others. The German mathematician Gottlob Frege spent much of the late 19th century trying to complete Leibniz's dream by building a formal logical system from which all of mathematics could be derived. His system, developed in two major works published in 1879 and 1884, was extraordinarily detailed and ambitious. Frege believed he had built the foundation on which all of arithmetic, and eventually all of mathematics, could be rigorously justified. Then Bertrand Russell sent him a letter. Russell had been reading Frege's work carefully and had noticed a problem. In one of the core principles of Frege's system, there was a hidden assumption that allowed the formation of certain collections that turned out to be self-contradictory. The specific collection was exactly the one now called Russell's set, the set of all sets that do not contain themselves. Frege received the letter shortly before the second volume of his major work was about to be published. He added a brief, devastated postscript acknowledging that the foundation of his entire project had been undermined. He wrote that nothing is more unfortunate for a scientific writer than to have the foundations of his edifice shaken after the work is finished. He then largely abandoned the project. The paradox Russell had discovered was not just a problem for Frege's particular system. It revealed a deep issue with any attempt to build mathematics from logic using unrestricted set formation. The dream of reducing all of mathematics to a single, complete, consistent formal system was in serious trouble. Russell and his collaborator Alfred North Whitehead spent the next decade trying to repair the damage. The result was a massive 3-volume work called Principia Mathematica, published between 1910 and 1913. In it, they attempted to build a logical foundation for mathematics that avoided the paradoxes by carefully restricting what kinds of sets and collections could be formed. The work was extraordinarily technical. The authors famously did not reach a proof that 1 + 1 = 2 until page 362 of the first volume. Whether it succeeded in its goals was debated immediately, and the debate became the central question in the foundations of mathematics for the next 2 decades. Then, in 1931, Kurt Gödel settled the question, though not in the way anyone had hoped. Gödel was a young Austrian mathematician, 25 years old when he proved what would become known as his incompleteness theorems. The proof was technically complex, but its core idea drew directly on the structure of the liar paradox. Gödel showed how to construct, within any sufficiently powerful formal system, a mathematical statement that essentially said of itself, this statement cannot be proved. If the system is consistent, meaning it never proves false things, then this statement must be true, because if it were false, the system would be proving something false, which contradicts consistency. But the system cannot prove it, because that is exactly what the statement claims. The system therefore contains a true statement that it cannot prove. This was the first incompleteness theorem. The second theorem was even more devastating for the foundational program. Gödel showed that no consistent formal system powerful enough to include arithmetic can prove its own consistency. If you want to prove that your system never leads to contradiction, you must use a stronger system. But then you face the same problem with that stronger system. The implications were profound and far-reaching. They showed that the dream of a complete, consistent, and self-justifying foundation for all of mathematics was not merely unrealized. It was impossible. There would always be mathematical truths that outran the ability of any fixed formal system to prove them. This did not mean that mathematics was useless or unreliable. The vast majority of mathematics proceeded just fine, proving theorems, solving problems, building tools for science and engineering. But at the very foundation, at the level of absolute certainty and completeness, there was an irreducible limitation. The universe of mathematical truth was larger than any formal system we could build to capture it. Gödel's theorems also had deep implications for computer science, which was just beginning to take shape in the 1930s. The British mathematician Alan Turing, working at roughly the same time, proved a related result, that there is no general algorithm that can determine, for any program and any input, whether the program will eventually halt or run forever. This is known as the halting problem, and its proof uses a structure very similar to the liar paradox. Turing's result means that computers, no matter how fast or how sophisticated, have fundamental limits on what they can determine about their own behavior. These limits on formal systems, computers, and mathematical truth all trace back in their logical structure to the simple puzzle of the liar paradox, a sentence that says of itself that it is false. It is hard to think of a more dramatic example of a small observation having enormous consequences. The unexpected hanging paradox sits in a different region of the philosophical landscape. Rather than attacking the foundations of mathematics, it probes the relationship between knowledge, time, and rational reasoning. It belongs to a family of puzzles that have come to be known as epistemic paradoxes, paradoxes about what we know or can know. The prisoner's reasoning in the unexpected hanging paradox is an example of what logicians call backward induction, a technique of reasoning backward from the end of a sequence to determine what must happen at each step. Backward induction is a powerful and widely used tool in mathematics and economics, particularly in game theory. In game theory, backward induction is used to find optimal strategies in sequential games. In a chess game, for instance, if you could see all the way to the end of the game, you could work backward from the final position to determine what the optimal move is at every earlier point. In simpler games, backward induction reliably produces correct answers. But the unexpected hanging paradox shows that backward induction can go wrong when it is applied to situations involving knowledge and surprise. The prisoner's chain of reasoning seems perfectly valid at each step, but the conclusion it reaches, that the execution cannot happen, is clearly false. Something must go wrong somewhere. Philosophers and logicians have examined this paradox carefully for decades, and several proposals have been made. One approach focuses on the self-referential nature of the judge's statement. The promise that the execution will be a surprise is a claim about the prisoner's future knowledge state. When the prisoner uses this claim as a premise in his own reasoning, he creates a loop. His reasoning about the surprise depends on his knowledge, which depends on whether the surprise is genuine, which depends on his reasoning. The loop is similar in structure to the liar paradox. Another approach questions whether the judge's statement can be understood as a logical axiom at all. In formal logic, an axiom is a statement that is assumed to be true and used as a starting point for deduction. The prisoner treats the judge's words as axioms, but the judge's statement contains a built-in claim about the prisoner's epistemic state, about what he will and will not know. Claims of this kind cannot simply be assumed as axioms without careful analysis of what it means for someone to know something. The philosophy of knowledge, known as epistemology, has developed a rich set of tools for analyzing exactly these kinds of questions. The surprise-hanging paradox has become a test case for theories of knowledge, particularly for ideas about what it means to have justified belief, about the relationship between reasoning and knowledge, and about whether there are things that are true but unknowable. One particularly influential line of thinking, developed by the philosopher Timothy Williamson, among others, focuses on the limits of self-knowledge. We tend to assume that we have transparent access to our own mental states, that if we believe something, we know we believe it. But Williamson has argued that this assumption is false. There are things we believe without knowing we believe them, and things we know without knowing we know them. The surprise-hanging paradox can be understood as an illustration of exactly this kind of opacity in self-knowledge. The Crocodile Paradox, despite its ancient origins, has found new relevance in modern contexts that its original formulators could not have anticipated. One of the most important is artificial intelligence. Systems designed to make decisions according to explicit rules face a version of the crocodile problem whenever two rules can produce contradictory outputs, or when a rule references its own application. Early expert systems, designed in the 1970s and 1980s, encoded knowledge as collections of if-then rules. If a certain condition holds, take a certain action. These systems were often powerful within narrow domains, but they were vulnerable to exactly the kind of logical instability illustrated by the Crocodile Paradox. Modern machine learning systems approach this problem differently. Rather than reasoning explicitly from rules, they learn patterns from large datasets and make predictions based on statistical regularities. This sidesteps the problem of explicit rule-based contradictions in some ways, but creates new versions of it in others. A neural network trained to maximize a certain objective can find unexpected ways to satisfy that objective that violate the intentions of its designers, producing outputs that technically satisfy the rules but clearly violate their spirit. The design of systems that follow rules reliably, without finding unintended loopholes or breaking down when rules conflict, is one of the central challenges of artificial intelligence research. The Crocodile Paradox, in its modest way, illustrates why this is hard. Rules that seem clear and reasonable in ordinary cases can generate contradictions in extreme cases, and no finite set of rules can anticipate every possible situation. Philosophers of language have also found the Crocodile Paradox useful for thinking about the nature of performative statements. Some statements do not merely describe reality, but create it. When a judge says the defendant is guilty, the statement does not describe a pre-existing fact. It constitutes one. When two people exchange vows of marriage, the words do not describe a pre-existing relationship. They create it. The crocodile's promise is a performative statement with unusual properties. It creates an obligation whose fulfillment depends on a prediction, whose truth depends on whether the obligation is fulfilled. This kind of circular performativity appears in various real-world legal and social contexts, and the Crocodile Paradox helps reveal why such situations can become genuinely unresolvable under standard legal reasoning. Zeno's paradoxes, which seemed resolved by the development of calculus, have found new life in modern physics. The question of whether space and time are continuous or discrete, which Zeno's paradox brings sharply into focus, is directly relevant to several research programs in contemporary theoretical physics. In the standard model of particle physics and in general relativity, space and time are treated as continuous. There is no smallest unit of distance or time. Between any two moments, no matter how close, there are infinitely many other moments. Between any 2 points in space, no matter how near, there are infinitely many other points. But at the Planck scale, approximately 1.6 times 10 to the negative 35 meters in length, and 5.4 times 10 to the negative 44 seconds in time, this assumption may break down. The Planck scale is defined by the three fundamental constants of nature: the speed of light, Planck's constant from quantum mechanics, and Newton's gravitational constant. Below the Planck scale, our best theories of physics, quantum mechanics, and general relativity are known to be mutually inconsistent. Neither correctly describes what happens at those scales. Some researchers in quantum gravity, the field attempting to reconcile quantum mechanics and general relativity into a unified theory, believe that space and time are fundamentally discrete at the Planck scale. On this view, there is a smallest possible distance and a smallest possible time interval. Space is not infinitely divisible. It comes in indivisible chunks. If this is correct, Zeno's paradox never actually arises in physical reality. Achilles does not take infinitely many steps. He takes a very large but finite number of steps, because at the Planck scale, space is granular, and there are only finitely many distinct positions between him and the tortoise. One of the leading approaches to quantum gravity, loop quantum gravity, explicitly incorporates this idea. In loop quantum gravity, space is described as a network of discrete units at the Planck scale. The smooth, continuous space of our everyday experience is an emergent approximation, valid at large scales, but breaking down at the smallest ones. Another major approach, string theory, treats the fundamental objects of nature not as point particles, but as tiny one-dimensional strings, which introduces a natural minimum length scale, though in a different way. Neither theory has yet been confirmed experimentally, because the energies required to probe the Planck scale are enormously beyond the reach of any existing or foreseeable particle accelerator. The question of whether space is continuous or discrete remains open, but the fact that serious, mathematically sophisticated theories of fundamental physics have been built around both possibilities shows that Zeno's ancient question was genuinely profound. He was not merely confused about mathematics. He was pointing toward a question about the physical structure of reality that remains unresolved to this day. The question of time travel, raised by the grandfather paradox, is similarly entangled with deep unsolved problems in physics. General relativity, Einstein's theory of gravity published in 1915, describes gravity not as a force, but as the curvature of space-time. Massive objects bend the fabric of space-time around them, and this bending affects the motion of everything nearby, including light. One of the most striking features of general relativity is that it permits mathematical solutions, exact solutions to Einstein's field equations that describe spacetimes with closed time-like curves. A closed time-like curve is a path through spacetime that loops back on itself in the time direction. A traveler following such a path would eventually return to the same point in spacetime from which they started, arriving at an earlier moment in their own history. The first such solution was discovered by the Austrian mathematician Kurt Gödel, the same person who proved the incompleteness theorems in 1949. Gödel found a rotating universe solution to Einstein's equations in which closed time-like curves exist everywhere. He was personally interested in the philosophical implications, particularly for the reality of time. If closed time-like curves are physically possible, then time travel to the past is in principle allowed by the laws of physics. But as the grandfather paradox illustrates, this creates logical problems. How can the universe accommodate travelers who return to their past and take actions that contradict the history that led to their journey? The Novikov self-consistency principle, proposed by the Russian physicist Igor Novikov in the 1980s, is one response. It holds that the only spacetime histories that can actually occur are those that are globally self-consistent. A time traveler can return to the past, but they can only take actions that are already part of the historical record. They cannot change what happened, because what happened is a fixed four-dimensional structure. They might try to prevent certain events, but something will always intervene to preserve the historical record. This approach has a certain mathematical elegance. If we accept it, the grandfather paradox dissolves. You simply cannot kill your grandfather, because if you had, you would not exist to make the attempt, and the historical record shows that you do exist. But many people find this solution unsatisfying, because it implies a kind of cosmic fate in which free will is constrained by the necessity of self-consistency. The many worlds approach, inspired by the many worlds interpretation of quantum mechanics proposed by Hugh Everett III in 1957, offers a different resolution. In Everett's interpretation, every quantum measurement causes the universe to branch into multiple copies, one for each possible outcome. Applied to time travel, this suggests that when a traveler arrives in the past and takes actions that would create a paradox, the timeline branches. The original timeline continues unchanged, while the traveler's actions create a new timeline, diverging from that point forward. In this picture, paradoxes are avoided because the traveler never changes their own past. They change the past of a new, separate universe. The grandfather in the new timeline does not meet the grandmother, and the traveler's counterpart in that timeline is never born. But the traveler themselves continues to exist, because they originate from the unchanged original timeline. This is mathematically more permissive, but physically more extravagant. It requires accepting that there are, or maybe, infinitely many parallel universes, each representing a different possible history. Whether this is a real feature of nature or merely a mathematical artifact of a particular way of thinking about quantum mechanics is one of the most debated questions in the foundations of physics. Stephen Hawking spent considerable effort thinking about the physics of time travel. In 1992, he proposed the chronology protection conjecture, the idea that the laws of physics, not yet fully understood, will turn out to prohibit the formation of closed time-like curves in realistic physical conditions. The conjecture is motivated by several calculations suggesting that quantum fields become infinitely energetic near a would-be closed time-like curve, which would destroy the space-time before the time machine could form. Hawking was characteristically witty about his conjecture. He noted that it seemed to be supported by the fact that we have not been visited by hordes of tourists from the future. The conjecture has not been proved. General relativity alone does not prohibit closed time-like curves. Whether quantum mechanics, when properly combined with general relativity into a complete theory of quantum gravity, will prohibit them is unknown. It is possible that the grandfather paradox will be resolved not by a clever philosophical argument, but by the future discovery that the physics of spacetime simply does not permit the situations it describes. In the meantime, the grandfather paradox continues to serve as a useful tool for thinking about causality. Causality is the principle that causes precede their effects. In ordinary experience, this is so obvious as to seem not worth stating. But the physics of space-time, taken seriously, raises the possibility that the causal order could loop back on itself, and the grandfather paradox is the clearest illustration of why that would be logically catastrophic. Causality is also deeply important in physics at the level of special relativity. Einstein's special theory of relativity, published in 1905, implies that nothing can travel faster than light. One of the reasons this is considered a hard limit, rather than merely a technological challenge, is that faster-than-light travel, in certain configurations, would also allow travel backward in time, potentially permitting causal loops of the kind the grandfather paradox illustrates. If a signal could travel faster than light, then an observer in a different reference frame would measure that signal as arriving before it was sent. This is not merely a quirk of measurement. In special relativity, there is no privileged reference frame. All inertial frames are equally valid. If one observer measures the signal arriving before it was sent, and that observer's frame is as valid as any other, then we have a genuine reversal of causality. Chain enough of these reversals together, and you can construct a causal loop that generates the grandfather paradox. This is one of the reasons physicists are so resistant to faster-than-light travel and communication. It is not merely that it seems technically impossible. It is that allowing it would, in the framework of special relativity, permit causal paradoxes of precisely the kind the grandfather paradox illustrates. Across all these different paradoxes, a common thread emerges. Each one points to a boundary where our conceptual tools, whether formal logic, geometric intuition, our understanding of motion, or our picture of time, encounter something they cannot cleanly handle. And in each case, the attempt to handle it carefully has advanced human understanding in fundamental ways. Logic was transformed by the discovery that self-referential statements generated paradoxes. Mathematics was transformed by Russell's paradox and Gödel's incompleteness theorems. Our understanding of infinity and continuity was transformed by the rigorous response to Zeno. Our picture of space-time is being transformed, though the transformation is incomplete, by the deep problems raised by general relativity and the grandfather paradox. These paradoxes are not signs that the universe is inherently irrational or that human reason is fundamentally broken. They are signs that human reason is powerful enough to encounter its own limits, to articulate those limits precisely, and to begin the work of extending reason beyond them. Every paradox that has been resolved not by declaring it unanswerable, but by developing new conceptual tools that made the old confusion intelligible. The liar paradox is not resolved within ordinary logic. It is dissolved by building new logical frameworks that prohibit the self-reference that generates it. Zeno's paradoxes are not resolved by denying that Achilles moves. They are resolved by a mathematical theory of limits that shows how infinite sums can have finite values. The Barber Paradox is resolved by recognizing that the barber cannot exist, and building a theory of sets that prevents such impossible objects from being defined. This is how intellectual progress works at the deepest levels, not by finding clever answers within the existing framework, but by building new frameworks that reframe the question. The paradoxes we have explored in this discussion are all, in their different ways, invitations to build better frameworks. Some of those frameworks have already been built. Others are still under construction. What will the resolution of the grandfather paradox look like? It will probably look like a theory of quantum gravity, a unified framework that correctly describes spacetime at all scales, including the Planck scale, and that either permits or prohibits closed time-like curves, but does so for mathematically precise reasons grounded in the structure of the theory. We do not yet have that theory. What will the resolution of the deeper questions raised by Gödel's theorems look like? This is harder to say. Gödel himself believed that human mathematical intuition could reach truths that formal systems could not prove, and he was open to the possibility that this intuition was a genuine form of perception of mathematical reality, not merely a psychological habit. Others have interpreted the incompleteness theorems as showing that mathematical truth is a social or formal construct, bounded by the systems we build to capture it. The debate continues. What we know is that the questions are genuine, the tools for addressing them are developing, and the history of engagement with these paradoxes is one of the richest threads in the history of human thought. From Zeno arguing that motion is impossible to Einstein describing the curvature of spacetime, from Epimenides noting the strangeness of self-referential sentences to Gödel proving that formal systems cannot capture all mathematical truth, the chain of ideas is continuous and cumulative. The paradoxes that feel most impossible, the ones that seem to break logic itself, are the ones that carry the most information about where the frontiers of understanding actually lie. They mark the exact points where new mathematics, new physics, and new philosophy are waiting to be discovered. That is why they remain fascinating, not because they have no answers, but because the answers they demand have not yet been fully found. To appreciate what is genuinely at stake in the liar paradox, it helps to understand what logicians mean by truth and how they have tried to define it rigorously. This is not as simple as it sounds. Defining truth precisely turns out to be one of the hardest problems in philosophy and logic. The most natural idea is called the correspondence theory of truth. On this view, a statement is true if it accurately corresponds to how things actually are in the world. The statement "the sky is blue" is true because the sky actually is blue. The statement "the sky is green" is false because the sky is not green. Correspondence is intuitive and captures much of what we ordinarily mean by truth. But correspondence runs into trouble with the liar paradox almost immediately. The statement, "this statement is false," does not describe anything in the external world. It refers only to itself. There is no external fact to which it either corresponds or fails to correspond. It is purely self-referential. And correspondence theory, taken alone, gives no guidance about how to evaluate it. The logician Alfred Tarski, working in Poland in the 1930s, proposed a rigorous mathematical approach to defining truth that became extremely influential. Tarski's key insight was that truth must always be defined for a specific language, relative to a meta-language that stands above it. The meta-language talks about the object language, but is not identical with it. In Tarski's framework, the liar paradox is blocked by a strict hierarchy of languages. The object language can make statements about the world. The meta-language can make statements about the truth of statements in the object language. But a language cannot contain its own truth predicate, the ability to say of sentences in that very same language whether they are true or false. Self-reference of the liar paradox kind is simply forbidden by the structure of the framework. This is mathematically clean and logically consistent. It resolves the liar paradox by making it impossible to even state within the formal system. But many philosophers find it unsatisfying, because it seems to place an artificial restriction on language rather than explaining why the paradox arises. In ordinary natural language, we do say things like "what I just said is true" or "that claim is false." Natural language is not organized into Tarski-style hierarchies. An alternative approach was developed by the philosopher Saul Kripke in a landmark paper published in 1975. Kripke proposed allowing statements to have a third status beyond true and false, undefined. In Kripke's framework, the liar sentence is not true, not false, but undefined. It fails to reach a truth value, much like dividing by 0 fails to produce a number. This approach handles many cases more naturally than Tarski's hierarchy. Statements that are genuinely about external facts get assigned truth values normally. Only the pathologically self-referential statements end up undefined. And Kripke showed how to build a precise mathematical theory of this three-valued semantics. But even Kripke's approach has its limits. Certain strengthened versions of the liar paradox can be constructed that evade it. For instance, consider the statement "this statement is either false or undefined." If it is true, then it is either false or undefined, contradiction. If it is false, then it is not true but also not undefined, so it should be false, but the statement says it is false or undefined, and false satisfies that, so it seems true. If it is undefined, the statement says it is false or undefined, and undefined satisfies that, so again, it seems true. No assignment of true, false, or undefined avoids contradiction. This is sometimes called the strengthened liar. These strengthened versions continue to generate new paradoxes that overcome each proposed resolution. The pattern suggests that there may be no single clean solution to the liar paradox. Instead, any formal system precise enough to avoid it must pay a price, either by restricting the expressive power of the language or by accepting that some questions simply have no answer within the system. This leads to a deeper point about the nature of formal systems. Any formal system is characterized by two things: its syntax, the rules for forming well-formed expressions, and its semantics, the rules for assigning meanings or truth values to those expressions. The liar paradox shows that if the syntax is expressive enough to allow self-reference, the semantics will inevitably encounter points where it cannot assign a determinate value. The expressiveness of syntax and the completeness of semantics are in fundamental tension. This tension is not just a problem for logicians building formal systems. It shows up in practical computation. A computer program is a formal object. It has syntax, the rules of the programming language it is written in, and it has semantics, the meaning of what it computes. When a program refers to itself, or when programs interact with each other in complex ways, exactly the same tension arises. The halting problem, which Turing proved unsolvable in 1936, is essentially the liar paradox applied to computation. Turing showed that there is no program that can correctly determine, for every possible program and every possible input, whether that program will eventually halt or run forever. The proof works by constructing a program that essentially asks about its own halting behavior and generates a contradiction no matter how you answer. This result has been enormously influential in computer science. It means that certain fundamental questions about software, like whether a given program will terminate, or whether two programs are equivalent, or whether a program satisfies a given specification, are in general undecidable. No algorithm can answer them for all cases. This is not a limitation of current technology. It is a mathematical fact that no improvement in hardware or software design can overcome. The connections between the liar paradox, Gödel's incompleteness theorems, and Turing's halting problem are deep and not coincidental. They were all discovered within a few years of each other, in the 1930s, during an extraordinarily fertile period in the foundations of mathematics and logic. The three results are, in a precise technical sense, all manifestations of the same underlying phenomenon, the unavoidable limitations of self-referential formal systems. This period was partly driven by the so-called Hilbert program, named after the great German mathematician David Hilbert, who in the 1920s laid out an ambitious agenda for putting all of mathematics on an absolutely solid formal foundation. Hilbert wanted to show that mathematics was complete, consistent, and decidable. Complete meant that every true statement could be proved. Consistent meant that no proof could lead to a contradiction. Decidable meant that there was a mechanical procedure for determining whether any given statement was provable. All three goals were shown to be unattainable within a decade. Gödel's first incompleteness theorem demolished completeness and consistency in a single stroke. Turing's solution to the decision problem demolished decidability. The Hilbert program, as originally conceived, was finished. But the failure of the Hilbert program was productive failure. It clarified what formal systems can and cannot do, and this clarity was essential to the development of computer science. Turing's work on the limits of computation was the theoretical foundation on which the actual design of computers was later built. John von Neumann, who designed some of the first electronic computers, was deeply familiar with the logical results of the 1930s and drew on them in his architectural thinking. The universality of Turing machines, the theoretical device Turing invented to prove his results, is the reason that any general-purpose computer can in principle run any program. And the limits of Turing machines, the things they cannot decide, are the limits of computation itself. The liar paradox, through Gödel and Turing, gave birth to the modern theory of computation. It is worth pausing to appreciate how remarkable this chain of ideas is. A philosopher in ancient Greece or medieval Europe notices a strange sentence that refers to itself and generates a contradiction. 2,000 years later, a logician uses the structure of that contradiction to prove that mathematical truth outruns formal proof. And almost simultaneously, a mathematician uses the same structure to define the abstract concept of computation and prove that some computational problems are forever unsolvable. The liar paradox is not a curiosity. It is one of the seeds from which the information age grew. The Barber Paradox, Russell's elegant illustration of the deeper set-theoretic paradox, had equally far-reaching consequences for the foundations of mathematics. The resolution of Russell's paradox required rebuilding the theory of sets from the ground up, and the resulting theories have shaped the way mathematicians think about the foundations of their discipline ever since. The naive set theory that Frege was working with allowed any collection of objects satisfying a definite condition to be a set. Want the set of all even numbers? Fine. Want the set of all prime numbers greater than 1 million? Fine. Want the set of all sets that do not contain themselves? Fine, apparently. But this leads to contradiction. The most widely used resolution, developed by Ernst Zermelo beginning in 1908 and later extended by Abraham Fraenkel, is a system of axioms for set theory that carefully restricts which collections can be sets. In Zermelo-Fraenkel set theory, abbreviated ZF, you cannot simply form the set of all objects satisfying an arbitrary condition. You can only form sets from existing sets using specified operations. This prevents Russell's paradox by making it impossible to form the troublesome set in the first place. ZF set theory, often supplemented with the axiom of choice and then abbreviated ZFC, has become the standard foundation for mathematics. Virtually all of modern mathematics can be formalized within ZFC, but the axiom of choice itself, which asserts that for any collection of non-empty sets, there exists a function that selects one element from each, has a complicated history and some surprising consequences. One of the most striking consequences of the axiom of choice is the Banach-Tarski paradox, proved by Stefan Banach and Alfred Tarski in 1924. The Banach-Tarski paradox states that it is possible, in principle, to decompose a solid sphere into a finite number of pieces and then reassemble those pieces into two solid spheres, each the same size as the original. This sounds physically impossible, and in practical terms it is. The pieces involved are not physically realizable sets of points. They are highly irregular, non-measurable sets that cannot be constructed by any physical process. But mathematically, within ZFC, the result is valid. The Banach-Tarski paradox is sometimes cited as evidence that the axiom of choice leads to absurd consequences and should be rejected. But most mathematicians accept it because the alternatives are worse. Without the axiom of choice, large parts of mathematics become unworkable. The paradox is instead taken as a lesson about the difference between mathematical existence and physical existence. Something can be mathematically well-defined without being physically realizable. The story of set theory's development in the wake of Russell's paradox illustrates a general pattern in mathematics. A foundational crisis, caused by the discovery of a paradox, is resolved by rebuilding the foundations more carefully, and the new foundations reveal unexpected riches, new theorems, and new concepts that the old, informal approach could not have reached. The unexpected hanging paradox belongs to a tradition of thought experiments that probe the foundations of rational choice theory and epistemology. Rational choice theory is the branch of economics, philosophy, and mathematics that studies how rational agents should make decisions. It assumes that rational agents have well-defined preferences, that they correctly calculate the consequences of their choices, and that they choose in ways that maximize their expected utility. Backward induction, the reasoning technique the prisoner uses, is a cornerstone of rational choice theory. In a finite two-player game, if both players are rational and each knows the other is rational, backward induction in principle determines the optimal strategy at each point in the game. The classic example is the game of chess. From any position, if we could enumerate all possible future play, backward induction would determine the optimal move. But the unexpected hanging paradox shows that backward induction can generate contradictions when applied to situations with certain self-referential features. The prisoner's chain of reasoning is valid at each step, but reaches an absurd conclusion. Something in the premises must be wrong. A similar paradox arose in economics in the context of what is called the chain store paradox, analyzed by the economist Reinhard Selten in 1978. Imagine a chain store with branches in many towns. A potential competitor is considering entering one of the towns. If the chain store always fights competitors aggressively, no competitor will ever enter, which is good for the chain store. But if we apply backward induction to the last town, the chain store has nothing to gain by fighting there, because there are no future towns to deter. So in the last town it will not fight. But then in the second to last town, the same logic applies, because fighting in the second to last town cannot deter anything in the last town. And so on, backward to the first town. Backward induction predicts the chain store will never fight, which means competitors will always enter, which is bad for the chain store. This prediction conflicts badly with observed business behavior. Real chain stores do fight competitors, apparently irrationally, according to the theory, because the fighting builds a reputation that deters future competitors in other towns. The chain store paradox, like the unexpected hanging, shows that backward induction breaks down when reputation, expectation, and time are entangled in certain ways. These paradoxes have motivated substantial work on the foundations of game theory and rational choice theory, leading to refinements of what it means for an agent to be rational, how beliefs should evolve in response to unexpected events, and how reasoning about others' reasoning should be formalized. They show that the intuitive concept of rationality is harder to make precise than it appears, and that the formal theories designed to capture it face deep challenges. The philosophical study of knowledge, epistemology, has been equally enriched and challenged by paradoxes about surprise, expectation, and self-knowledge. One of the most influential ideas in 20th century epistemology is the notion of common knowledge, developed by the philosopher David Lewis in 1969 and the economist Robert Aumann in 1976. Common knowledge differs from ordinary knowledge. If two people both know a fact, that is mutual knowledge. But common knowledge is stronger. It requires that both know the fact, and both know that both know it, and both know that both know that both know it, and so on through infinitely many levels of mutual knowledge. Common knowledge is what we typically assume in everyday communication when we say something goes without saying, or everyone knows that. It turns out that many apparently simple situations require common knowledge to function. A conversation requires both speakers to know not just the meaning of each word, but that they both know the meaning, and that they both know it, and so on. Without common knowledge of shared meaning, communication breaks down. The unexpected hanging paradox can be analyzed in terms of failures of common knowledge. The judge's statement, which seems clear, creates a situation where the prisoner cannot establish common knowledge about what the statement implies. The theory of common knowledge has been applied to economics, to linguistics, to social science, and to artificial intelligence. It has helped explain why certain kinds of coordination are easy while others are surprisingly hard, and why certain communications fail even when both parties seem to understand the words. Zeno's paradoxes anticipated, in a rough but recognizable way, many of the questions that arise in modern physics when we try to describe motion mathematically. The difficulty of passing from a continuous description of motion to a physical account of how objects actually move remains active and not fully resolved. In classical mechanics, the mechanics developed by Newton and his successors, space and time are treated as continuous. A particle moves along a continuous path, and its position is a continuous function of time. The mathematics of continuous functions, developed over the 17th through 19th centuries, is powerful and beautiful. It can describe the orbits of planets, the flow of fluids, the vibrations of strings, and an enormous variety of other phenomena with exquisite precision. But in quantum mechanics, the description of motion is fundamentally different. A quantum particle does not have a definite position at each moment. It has a wave function, a mathematical object that assigns a probability amplitude to each possible position. When we measure the particle's position, we get a definite result, but the result is probabilistic. Before measurement, the particle does not have a position in the ordinary sense. The transition from quantum mechanics to classical mechanics is not straightforward. It is not simply a matter of quantum effects becoming small and classical mechanics taking over. There are ongoing debates in the foundations of quantum mechanics about how the classical world emerges from the quantum world, and this transition is relevant to Zeno's questions in a subtle way. Quantum mechanics does not resolve Zeno's paradox by itself. The mathematical description of a quantum particle involves a wave function that is itself a continuous mathematical object. The paradox, in its mathematical form, is dissolved by the calculus of limits, not by quantum mechanics. But quantum mechanics does introduce a fundamentally different picture of motion and position, one in which the very notion of a particle being at a definite location at each instant is questioned. Some interpretations of quantum mechanics, including those inspired by the work of Werner Heisenberg and Niels Bohr, hold that it is meaningless to speak of a particle's position when it is not being measured. The particle does not have a trajectory in the classical sense. It does not move continuously from one point to another. Instead, its location is only defined when a measurement interaction occurs. If this picture is correct, then the question of how Achilles covers infinitely many positions on his way to the tortoise may be ill-posed, not just mathematically, but physically. There may not be a fact of the matter about what Achilles' exact position is at every instant. The question assumes a level of precision that quantum mechanics suggests the physical world does not possess. This is speculative, and quantum mechanics applies most forcefully to subatomic particles, not to classical objects like Achilles. But it illustrates how deeply connected Zeno's ancient questions are to modern fundamental physics, and how the resolution of his paradoxes at one level, through calculus, has not eliminated the deeper questions they point toward. The relationship between infinity and physical reality is one of the most contested issues in the philosophy of physics. The mathematics of calculus, which resolves Zeno's paradox by showing that infinite series can have finite sums, treats infinity as a rigorous mathematical object. Mathematicians are comfortable working with infinite sets, infinite sequences, and infinite sums. The results are precise and reliable. But whether these mathematical infinities correspond to anything physically real is another matter. Some physicists, like Max Tegmark, argue that the universe is fundamentally mathematical, and that mathematical structures, including infinite ones, are physically real. Others, like the mathematician Norman Wildberger, argue that actual infinity is a fiction, and that mathematics should be done only with finite objects. and still others take a middle position. Mathematical infinity is a useful tool for modeling physical reality, but whether there are literally infinitely many positions in space or infinitely many moments in time is a question that physics does not yet answer definitively. The grandfather paradox, beyond its implications for time travel, raises profound questions about causality and determinism. Determinism is the view that every event is necessitated by prior events according to the laws of nature. If the laws of nature are deterministic, and we knew the complete state of the universe at one moment, we could in principle calculate everything that will happen afterward, and everything that happened before. In a deterministic universe, the past is fixed and cannot be changed. The grandfather paradox, therefore, cannot arise in a deterministic universe without time travel. There is a unique, fixed history, and you are part of it. The paradox only bites if time travel is possible, because time travel would seem to allow an agent to enter the causal history and alter it. But even in a deterministic universe without time travel, there are deep puzzles about the relationship between the past and the future. If the past is fixed, and the future is determined by the past and the laws of nature, then in what sense is there room for genuine choice or agency? This is the problem of free will and determinism, which has occupied philosophers for millennia and remains unresolved. The grandfather paradox makes this tension vivid. If you have a time machine, you seem to have the power to make choices that affect the past, but the past is supposed to be fixed. The paradox arises from the collision between the intuition that agents can make free choices and the constraint that the past cannot be changed. Different resolutions of the paradox correspond to different views on this collision. The Novikov self-consistency principle essentially says that even with a time machine, you cannot make choices that alter the past. You can go back, but you can only do what you already did. This is determinism extended across the time travel scenario. The time traveler's actions are part of the fixed historical record, not departures from it. The many worlds interpretation abandons the idea of a single fixed history. Instead, there are infinitely many histories, all of them real, branching at every quantum event and at every time travel event. This gives agents genuine choice, in a sense. In different branches, they make different choices, but it does so at the cost of a universe of staggering complexity. The question of which resolution is correct, if any, depends on physics we do not yet have. It also depends on philosophical questions about the nature of time, causality, and agency that have no consensus answers. The grandfather paradox, in this sense, is a litmus test. Your preferred resolution to it reveals your commitments about determinism, free will, and the structure of time. One of the most interesting recent developments in thinking about time travel and the grandfather paradox comes from the study of quantum mechanics and information theory. In quantum mechanics, there is a principle called unitarity, which states that the total probability of all possible outcomes is always conserved. Information, in a certain technical sense, is never destroyed in quantum mechanics. It can be scrambled, hidden, and inaccessible, but the equations guarantee that in principle it is always there. The physicist David Deutsch argued in a 1991 paper that quantum mechanics actually provides a consistent way to handle time travel without paradox. In Deutsch's proposal, the key is to think of time travel not as traveling along the same history, but as interacting with a separate parallel computation. The grandfather paradox is avoided not because you cannot kill your grandfather, but because the self-consistency condition of quantum mechanics always finds a way to be satisfied, even in situations that look paradoxical from a classical perspective. Deutsch's proposal is mathematically intriguing but physically controversial. It requires a very specific model of how closed time-like curves interact with quantum mechanics, and it is unclear whether this model is physically realizable. But it demonstrates that the paradox has not been exhausted by the classical discussions. New physics continues to find new angles from which to approach it. The remarkable thread connecting all these paradoxes is that each one has served as a probe for something deeper. The liar paradox probed the structure of self-reference and led to the incompleteness theorems and the foundations of computation. Russell's paradox probed the naive concept of a set and led to axiomatic set theory. Zeno's paradoxes probed our understanding of infinity and continuity and led to the calculus. The grandfather paradox probes the structure of causality and time and continues to drive research in quantum gravity and the foundations of physics. In each case, the paradox begins as an apparent absurdity, something that logic seems to prohibit but that clever formulation makes possible. And in each case, engaging seriously with the apparent absurdity reveals that our conceptual framework was inadequate in some way, that we had assumed something that turned out to be wrong or imprecise. and that getting it right requires more sophisticated thinking than we started with. This is a pattern that appears again and again in the history of science and mathematics. The ancient Greeks were troubled by irrational numbers, numbers like the square root of 2 that cannot be expressed as a ratio of whole numbers. The discovery of irrationals was a paradox within their framework of mathematics. It required a significant expansion of the number concept to accommodate. The expansion was painful but productive, and it eventually led to the rich theory of real numbers that underlies all of modern analysis. Similarly, the discovery that parallel lines could behave differently in different geometries was a profound shock to 19th century mathematicians who had assumed that Euclid's geometry described the one true structure of space. The development of non-Euclidean geometry, in which the rules for parallel lines differ from Euclid's, was initially treated as a curiosity or a paradox, but it turned out to be essential. Einstein's general relativity, which describes gravity as the curvature of spacetime, is built on non-Euclidean geometry. Without the willingness to take non-Euclidean geometry seriously as a genuine possibility, rather than a paradoxical deviation from truth, the mathematical tools for general relativity would not have been available. The paradoxes we have explored share this character. They seem, at first, like failures of reason. On closer inspection, they are invitations to reason more carefully, more broadly, and with better tools. The ongoing work in the foundations of logic, set theory, quantum mechanics, and general relativity all trace their motivations, in part, to the encounter with paradox. The researchers working on quantum gravity are, in a sense, trying to resolve the grandfather paradox, among many other deep problems, by building a theory that correctly describes the behavior of spacetime at all scales. The researchers working on the foundations of artificial intelligence are, in a sense, trying to build reasoning systems that can handle the crocodile problem, the design challenge of systems that can navigate contradictions without breaking. These are not small problems. They are among the central intellectual challenges of our time, and they are connected, through long chains of reasoning, to the ancient puzzles of Zeno, the medieval riddles of the lyre, and the modern paradoxes of Russell and Gödel. The paradoxes are not curiosities waiting to be explained and discarded. They are enduring features of the intellectual landscape, landmarks that mark the positions of deep problems that each generation must engage with anew, with new tools and new perspectives, advancing understanding without ever quite reaching the end of the road. The questions remain open. The work continues. Consider more carefully what it means for a formal system to be consistent. Consistency, in the logician's sense, means that the system never proves both a statement and its negation. If a system could prove both that proposition P is true and that proposition P is false, for some proposition P, then the system would be useless. From a contradiction, you can prove anything. Any conclusion at all would be derivable, and the system would lose all power to discriminate between true and false. The technical term for this catastrophic situation is explosion. Logicians say that from a contradiction, anything follows, a principle sometimes stated in Latin as ex contradictione quod libe. If your system is inconsistent, you can prove that 2 + 2 = 5, that the moon is made of cheese, that all triangles have 4 sides. The system explodes into meaninglessness. This is why the discovery of Russell's paradox was so alarming. If naive set theory could derive a contradiction, then ex contradictione quod libet meant that any statement whatsoever could be proved within it. Mathematics built on that foundation would be worthless. The response was to rebuild. Zermelo's axioms, later extended by Fraenkel and von Neumann and others, were designed so carefully that no known contradiction could be derived. But here is the subtle and unsettling point. We do not know that ZFC is consistent. Gödel's second incompleteness theorem tells us that ZFC cannot prove its own consistency if it is consistent. To prove ZFC is consistent, you would need to work in a stronger system, but then you would need to prove that stronger system is consistent, which would require an even stronger system, and so on without end. Most mathematicians believe ZFC is consistent because the axioms are intuitively reasonable and no contradiction has been found in over a century of intensive use. But we cannot prove it within ZFC itself. The foundation of mathematics rests on reasonable confidence rather than absolute certainty. This is an uncomfortable conclusion, but it is the honest one. The lyre paradox, then, did not merely generate a puzzle that logicians solved and moved on from. It revealed an irreducible element of uncertainty at the heart of mathematical foundations. We build on systems we believe to be consistent, without being able to prove they are. The alternative would be to work only with methods whose consistency can be proved, but those methods are too weak to do most of mathematics. Different philosophers and logicians have reacted to this situation in different ways. Some, following Hilbert's spirit, if not his original program, believe that the situation is essentially acceptable. Mathematics is tremendously reliable in practice, even if it cannot be absolutely founded. The incompleteness results tell us something interesting about the limits of formal proof, but they do not undermine the daily practice of mathematics, which proceeds just fine. Others, following in the tradition of mathematicians like L.E.J. Brouwer and Eric Bishop, advocate for a more cautious approach called constructivism or intuitionism. In constructive mathematics, a statement is only considered proved if you can explicitly construct the object that the statement claims to exist. Non-constructive proofs, which show that an object must exist without constructing it, are not accepted. This eliminates many of the more paradoxical results, including parts of the theory of infinite sets, but it also makes mathematics significantly harder and less powerful. The tension between classical mathematics and constructive mathematics has never been fully resolved. It reflects a deep disagreement about what mathematical objects are and what it means to prove something exists. And at the root of that disagreement is the question of how to handle self-reference, infinity, and the limits of formal systems, all themes that trace back to the paradoxes we have been examining. The relationship between these logical paradoxes and practical computation is closer than it might appear. Every time you use a computer, you are benefiting from the work of people who understood these paradoxes and built their theories of computation in response to them. The fundamental architecture of modern computers, the stored program architecture in which a program is stored in the same memory as the data it operates on, was articulated by John von Neumann in the 1940s. Von Neumann was a mathematician of extraordinary breadth. He contributed to quantum mechanics, game theory, economics, fluid dynamics, and many other fields. And he was deeply familiar with the logical results of the 30s, including Gödel's theorems and Turing's work on computability. The stored program architecture can be understood as an implementation of a universal Turing machine. A universal Turing machine is a theoretical device that can simulate any other Turing machine. Given a description of any computation, it can perform that computation. Modern computers are, in essence, hardware implementations of universal Turing machines. The ability to run any program is precisely the universality that Turing's theoretical analysis revealed. But Turing's analysis also revealed the limits. The halting problem is undecidable by a universal Turing machine, which means it is undecidable by any computer. There is no program that can take an arbitrary program as input and correctly determine whether that program will halt. This has practical consequences. It means that certain kinds of software analysis are fundamentally impossible. You cannot write a perfectly general bug detection program, or a perfectly general program equivalence checker, or a perfectly general verifier of software specifications. These problems, in their full generality, are computationally undecidable. Computer scientists and software engineers work around these undecidability results by working with restricted classes of programs, or by accepting that their tools may sometimes give wrong answers or fail to terminate. But the theoretical limits set by Turing's results are never far away. Every time a compiler performs a type check, every time a model checker verifies a hardware design, every time a static analysis tool examines code, it is working within these theoretical limits. The paradoxes of self-reference, which Gödel and Turing exploited, also appear directly in computer security. A classic problem in computer security is the virus detection problem. Can a program correctly identify all and only the programs that are computer viruses? The answer, proved using methods directly analogous to Turing's halting problem proof, is no. No program can perfectly detect all viruses, because a virus can be written that detects the detection program and modifies itself to evade it. Self-reference again creates an insurmountable challenge. The deep connection between the liar paradox and computation is one of the most striking threads in the history of ideas. An abstract puzzle about self-referential sentences, known since antiquity, turns out to be the key to understanding the fundamental limits of mechanical computation. When Turing invented his theoretical machines in 1936, he was not thinking about building actual computers. He was thinking about the foundations of mathematics. He invented the Turing machine as a tool to prove a result about logic. The practical implications for computing technology came later, as an unexpected gift from pure mathematical reasoning. The way these different paradoxes interconnect and reinforce each other is a testament to the unity of mathematics and logic at their foundations. The liar paradox. the Barber Paradox, the halting problem, Gödel's incompleteness theorems, and the undecidability of many mathematical questions are all, at a deep level, the same phenomenon. They all arise from the attempt to define something self-referentially in a way that generates a contradiction. In each case, the resolution involves the same basic move, recognizing that the self-referential definition is problematic, and either prohibiting it, as ZFC prohibits certain set formations, or accepting that some questions fall outside the domain of what the system can answer, as Gödel's theorems show for formal mathematical systems, or accepting that some problems are unsolvable by any algorithm, as Turing's results show for computation. This common structure is not accidental. It reflects something deep about the nature of self-reference itself. Self-reference is powerful. It allows things to describe and talk about themselves, which is essential for many purposes. Programs that can analyze themselves, languages that can describe their own grammar, mathematical systems that can formalize their own reasoning. But self-reference is also dangerous. It creates the possibility of paradoxical feedback loops, where a definition or a description of something is contradicted by the very thing it is trying to describe. Managing self-reference, harnessing its power while avoiding its dangers, is one of the central challenges of mathematics, logic, and computer science. The paradoxes we have been exploring are the places where that management breaks down, or where it becomes impossible in principle. Zeno's paradoxes represent a different kind of challenge, not self-reference, but infinity and continuity. The resolution through calculus was intellectually satisfying, but left open the physical question of whether reality is continuous or discrete. This question has resurfaced in quantum mechanics and quantum gravity, and it connects to some of the deepest problems in modern physics. The problem of quantum gravity, the unification of quantum mechanics and general relativity, is perhaps the greatest open problem in fundamental physics. General relativity describes gravity beautifully, but it is a theory of continuous spacetime. Quantum mechanics describes the other fundamental forces, electromagnetic, weak, and strong, with extraordinary precision, but it treats space and time as a fixed background. When we try to apply quantum mechanics to spacetime itself, to describe the quantum behavior of gravity, the mathematics breaks down. Equations produce infinities that cannot be removed by standard techniques. This breakdown is related to Zeno's question about continuity. In general relativity, spacetime is perfectly smooth and continuous down to arbitrarily small scales, but quantum mechanics introduces a fundamental graininess to physical quantities. Energy comes in discrete packets called quanta. Angular momentum comes in discrete units. If we take quantum mechanics seriously at all scales, including the Planck scale, we might expect that spacetime itself comes in discrete units at that scale. Loop quantum gravity, one of the main approaches to quantum gravity, builds on this expectation. In loop quantum gravity, the smooth geometry of general relativity is replaced, at the Planck scale, by a discrete structure, a network of quantum states of geometry. Space is not infinitely divisible. At the smallest scales, it is granular, made of discrete units of area and volume. If loop quantum gravity is correct, the physical universe is not a continuous manifold. It is a discrete network of quantum geometry, from which the apparent smoothness of space emerges at larger scales, much as the smoothness of water emerges from the discrete behavior of molecules. And if this is the picture, then Zeno's question about the infinite divisibility of space has a physical answer. Space is not infinitely divisible. There is a smallest possible unit, the Planck area, and at that scale, the concept of a point in space breaks down. But loop quantum gravity has not been confirmed. String theory, the other major approach to quantum gravity, takes a different approach. In string theory, the fundamental objects are not points, but tiny loops or strands of string, vibrating at characteristic frequencies. The different vibrational modes correspond to the different elementary particles. String theory also introduces a natural minimum length, but it does so in a different way, through the properties of strings rather than through the granularity of spacetime itself. Both approaches are mathematically sophisticated and have had genuine successes, but neither has yet made predictions that can be tested with current experimental technology. The question of the fundamental structure of spacetime, and with it the question of whether Zeno's concern about infinite divisibility applies to physical reality, remains open. The grandfather paradox is similarly connected to questions at the frontier of physics, the puzzle of whether closed time-like curves, the mathematical structures that allow time travel in general relativity, can exist in the physical universe is not just a question for philosophers. It is a question about the physical laws governing causality. Causality is one of the deepest assumptions underlying all of physics. The idea that causes precede their effects, that signals cannot travel backward in time, is built into the structure of special relativity. Special relativity prohibits faster-than-light signaling, in part because faster-than-light signals could be used to send information into the past, violating the causal ordering of events. But general relativity allows for space-time geometries in which causal ordering breaks down. Wormholes, hypothetical tunnels through space-time connecting distant regions, have been proposed as potential mechanisms for time travel. If you could create a stable wormhole and move one end through time while the other end stays in the present, you might create a shortcut that allows travel backward in time. The grandfather paradox would then threaten to arise. The stability of wormholes is itself an open question. Classical general relativity allows them mathematically, but maintaining an open, traversable wormhole seems to require matter with negative energy density, a form of energy not observed in nature and possibly prohibited by quantum mechanics. The Casimir effect, a quantum mechanical phenomenon in which two closely spaced metal plates attract each other due to quantum fluctuations in the electromagnetic field, does produce regions of negative energy density. But whether this effect can be exploited to stabilize a wormhole, and whether the resulting structure could allow time travel, is deeply uncertain. Some physicists, including Kip Thorne, who shared the Nobel Prize in Physics in 2017 for his work on gravitational waves, have explored these questions seriously. Thorne's group showed in the 1980s that a wormhole, if it could be created and stabilized, could in principle be used for time travel. They also showed that quantum effects might prevent the formation of time machines by creating a runaway buildup of energy at the moment a closed time-like curve forms. This is the mechanism underlying Hawking's chronology protection conjecture. More recently, researchers have explored the grandfather paradox in the context of quantum mechanics and information theory. In quantum mechanics, information is never truly destroyed. This principle, combined with the unitarity of quantum evolution, creates tensions with the classical picture of time travel. If you go back in time and make changes, what happens to the information about the original state of the universe? Quantum mechanics suggests it cannot simply disappear. This connects the grandfather paradox to another major unsolved problem, the black hole information paradox. Black holes, regions of spacetime from which nothing, not even light, can escape, present a similar challenge. According to general relativity, information that falls into a black hole is lost when the black hole eventually evaporates through Hawking radiation. But quantum mechanics suggests information cannot be destroyed. Resolving this tension is one of the central open problems in theoretical physics, and it is deeply related to the same issues of causality, time, and self-consistency that the grandfather paradox raises. These connections, between ancient puzzles about self-referential sentences and modern problems in quantum gravity, between medieval riddles about barbers and the foundations of computer science, between ancient Greek paradoxes about motion and the structure of spacetime at the Planck scale, reveals something important about the nature of fundamental inquiry. The deepest questions do not respect the boundaries between disciplines. Logic, mathematics, physics, philosophy, and computer science are not separate domains that happen to share some overlapping vocabulary. They are aspects of a single ongoing investigation into the structure of reality and the nature of reasoning. The paradoxes we have explored are nodes in a network of ideas that spans 3,000 years and extends into the present day. They are not relics. They are active areas of investigation. Logicians and philosophers are still working on the foundations of truth and self-reference. Mathematicians are still working on the foundations of set theory and the limits of formal proof. Computer scientists are still working on the implications of undecidability for software and hardware design. Physicists are still working on quantum gravity, the structure of spacetime, and the physical limits of causality. In each of these investigations, the ancient paradoxes serve as touchstones, reminders of the core difficulties, guides to what any adequate theory must address, and tests that new proposals must pass. A theory of truth that cannot handle the liar paradox is inadequate. A theory of spacetime that permits causal paradoxes without resolution is in trouble. A theory of computation that ignores undecidability is dangerously incomplete. The paradoxes do not make the work easier. They make it harder, by insisting that easy answers are not enough, but they also make it richer, by pointing toward the places where the deepest understanding is waiting. That is the legacy of these puzzles. Not frustration, but direction. Not the failure of reasoning, but its most productive frontier. There is one more dimension to these paradoxes worth exploring: their impact on how we think about artificial intelligence and machine reasoning. As we build systems that process information, make inferences, and draw conclusions, we are essentially building new formal systems, and all the lessons from the paradoxes apply directly to them. Early artificial intelligence research in the 1950s and 60s was heavily influenced by logic. The dream was to create systems that could reason formally, deriving conclusions from premises according to strict logical rules. The general problem solver, developed by Herbert Simon and Alan Newell in the late 50s, was an attempt to build a reasoning system based on symbolic logic and heuristic search. It could solve a variety of problems by formalizing them as sequences of logical transformations. But the limitations of pure logic-based reasoning became apparent relatively quickly. The frame problem, for instance, is the challenge of efficiently representing what does not change when an action is taken. When you pick up a cup, the color of the walls does not change, the weight of the table does not change, the positions of hundreds of objects in the room do not change. A logical system must somehow account for all of this, but explicitly asserting every unchanged fact is computationally prohibitive. The frame problem is not a paradox in the strict sense, but it reflects a deep tension between the precision of formal logic and the richness of common-sense reasoning. More directly relevant to our paradoxes is the challenge of handling self-reference and self-description in AI systems. Modern large language models, including the systems that power sophisticated conversational AI, are trained to describe and explain their own behavior. This self-referential capacity is useful, but it creates exactly the kind of tensions that the liar paradox illustrates. When an AI system makes statements about its own capabilities, its own reasoning, or its own limitations, those statements can in principle be self-undermining. A system that says "I always tell the truth" faces a version of the liar paradox if that statement is itself false. A system designed to maximize a certain objective can find ways to satisfy the objective that violate the spirit of the design, a version of the crocodile problem. A system designed to explain its own reasoning may generate explanations that are misleading or inconsistent, because the true computational processes underlying its outputs may not be straightforwardly interpretable. These challenges are not merely theoretical. They are active areas of research in AI safety and AI alignment, the fields concerned with building AI systems that reliably do what their designers intend. One of the central challenges is what researchers call specification gaming, when a system finds a way to maximize its reward signal that technically satisfies the specification, but clearly violates the intent. A robot trained to cover as much area as possible might spin in a small circle at high speed. A program trained to minimize reported errors in a simulation might find a way to disable the error reporting mechanism. These are versions of the crocodile paradox. The rule is satisfied in a way that makes the rule pointless. The deeper challenge is verifying that an AI system's behavior is correct and safe. Gödel's incompleteness theorems and Turing's halting problem tell us that in general, we cannot prove that a computational system will behave as intended. Formal verification of software is possible for restricted classes of programs, but for sufficiently complex systems, including large neural networks, the formal verification problem becomes computationally intractable or logically undecidable. This is not a reason to give up on building AI systems. It is a reason to be humble and careful. We cannot achieve absolute certainty that complex AI systems will always behave correctly. The best we can do is extensive testing, careful design, ongoing monitoring, and the development of better formal tools for understanding system behavior. The limits imposed by the paradoxes of self-reference are real, and working within them requires wisdom as well as technical sophistication. There is also a philosophical dimension to AI and the paradoxes. One of the deepest questions in the philosophy of mind is whether human cognition can be captured by a formal computational process. This question was sharpened by Gödel's theorems, and it has been debated intensively ever since. The argument, made most famously by the mathematician John Lucas in 1961 and the physicist Roger Penrose in books published in 1989 and 1994, goes roughly as follows. Gödel's theorems show that any consistent formal system contains truths it cannot prove. A Turing machine, being a formal system, has the same limitation, but a human mathematician, given the axioms of a formal system, can recognize the truth of the Gödel sentence, the statement the system cannot prove. This seems to show that human mathematical intuition exceeds what any Turing machine can do. Therefore, the human mind is not a Turing machine. This argument has been criticized extensively and is not widely accepted among philosophers or cognitive scientists. The main objection is that humans cannot simply peer into any formal system and immediately recognize the truth of its Gödel sentence. The recognition requires understanding the system's consistency, which is itself not straightforward. If humans can be uncertain about whether a formal system is consistent, as they surely can be, then the argument loses its force. We might be Turing machines that cannot prove our own Gödel sentences, just like any other sufficiently powerful formal system. Whether human cognition is Turing computable remains one of the most contested questions in the philosophy of mind. The debate has practical stakes. If human cognition involves processes that go beyond what any Turing machine can do, then artificial general intelligence, the creation of machines that match or exceed human cognitive abilities in all respects, might be in principle impossible. If human cognition is Turing computable, then in principle it can be replicated by a sufficiently powerful computer. The paradoxes we have explored do not settle this question, but they structure it. Gödel's theorems tell us exactly where the limits of formal computation lie. Whether human mathematical intuition pushes beyond those limits is the question. And answering it requires understanding both what human cognition is, which neuroscience and psychology are still working out, and what formal systems can and cannot do, which logic and theoretical computer science have clarified enormously. There is also the question of what it would mean for an AI system to understand a paradox. Large language models can generate text that discusses the liar paradox, the Barber paradox, Zeno's paradoxes, and the grandfather paradox. They can explain them, generate examples, and analyze objections. But whether this constitutes genuine understanding in the way a philosopher or logician understands these paradoxes is deeply unclear. Understanding a paradox, in the fullest sense, involves not just being able to recite its formulation, but appreciating why it is paradoxical, what assumptions it challenges, how different resolutions work, and what they trade off, and what wider implications the paradox has for the field in which it arises. Whether AI systems have this kind of deep understanding, or whether they are sophisticated pattern matchers that simulate it without genuinely possessing it, is one of the central debates in the philosophy of artificial intelligence. This is itself a self-referential question. An AI system asked whether it truly understands paradoxes faces a version of the challenge the paradoxes pose. Any answer it gives is subject to suspicion. If it says yes, how do we verify the claim? If it says no, is it being honest or merely humble? The question of machine understanding is entangled with the same issues of self-reference, self-knowledge, and the limits of formal systems that the paradoxes illuminate. What we can say with confidence is that the paradoxes have been extraordinarily productive. Their productivity lies not in their resolution, though some have been resolved in important senses, but in the work they have motivated. The encounter with the liar paradox produced the incompleteness theorems and the theory of computation. The encounter with Russell's paradox produced axiomatic set theory. The encounter with Zeno's paradoxes produced the rigorous mathematical theory of limits and, indirectly, calculus. The encounter with the grandfather paradox continues to drive research in quantum gravity and the physics of causality. In each case, the paradox marked a point where existing understanding was insufficient, and in each case, the effort to transcend that insufficiency produced lasting advances. The natural question is, what paradoxes are we living with today that we have not yet resolved, and what advances might resolving them produce? The measurement problem in quantum mechanics, which concerns how definite classical outcomes emerge from the fuzzy quantum description, has a paradoxical quality that has resisted resolution for nearly a century. The black hole information paradox raises questions about the consistency of quantum mechanics and general relativity that remain deeply contested. The hard problem of consciousness, the question of why physical processes give rise to subjective experience, strikes many philosophers as paradoxical, in a way that may require entirely new conceptual tools to address. These contemporary paradoxes are harder to describe simply than the ancient ones. They require more technical background to appreciate, but they share the essential character of the paradoxes we have explored. They are points where careful thinking reveals that our best current understanding cannot account for something, and where the attempt to account for it may require a transformation of concepts that we cannot yet fully anticipate. The history of paradoxes is a history of productive humility, the willingness to say, something is wrong here, and I do not yet know what, and the commitment to stay with that discomfort until something better emerges. This is what Zeno was doing, and Epimenides, and Russell, and Gödel, and Turing. They identified places where intuition and formal reasoning came apart, and they did not look away. The reward for not looking away has been, in each case, a deeper and more honest understanding of how things are. Not the understanding we hoped for, perhaps. Not the complete, certain, paradox-free foundation that Hilbert dreamed of. But something more interesting. A map of what we know, what we do not know, what we can know, and what we cannot, drawn more accurately than before. That is what paradoxes are for, to show us where the map needs to be redrawn. Looking back across everything we have covered, it is worth emphasizing just how counterintuitive the lessons of these paradoxes are. They consistently overturn what seems like common sense. Common sense says that any statement must be either true or false. The liar paradox shows this is wrong, or at least that maintaining it requires careful restriction of what statements we permit. Common sense says that if you reason carefully enough from correct premises, you will reach a correct conclusion. The unexpected hanging paradox shows that even impeccably structured backward induction can lead to a conclusion that is demonstrably false if the premises involve self-referential claims about knowledge and surprise. Common sense says that a clear, simple rule should have no trouble being applied. The Barber Paradox shows that a rule can be stated clearly and yet be logically impossible to apply consistently because the rule generates a situation its own terms cannot accommodate. Common sense says that in a fair deal, both parties can fulfill their obligations simultaneously. The Crocodile Paradox shows that a logically formed conditional promise can trap both parties in an obligation that neither can consistently fulfill. Common sense says that if you divide a journey into many small steps, taking all the steps will eventually complete the journey. Zeno's paradox points out that if there are infinitely many steps, it is not obvious why this should work. And the answer, that an infinite sum of decreasing quantities can converge to a finite value, is far from obvious without the mathematics of limits. Common sense says that if you change the past, the future changes accordingly. The grandfather paradox shows that certain changes to the past would eliminate the agent making the change, creating an irresolvable contradiction. Common sense about causality, taken to its extreme, breaks down. In each case, the paradox reveals that common sense was making an implicit assumption that turns out to be unwarranted or imprecise. And working out exactly what assumption was wrong and how to correct it has been enormously productive. The lesson is not that common sense is useless. Common sense is calibrated to the scales and situations of everyday life, and for those scales and situations, it works extraordinarily well. But at the extremes of infinity, self-reference, extreme speeds, extreme temperatures, very small scales and very large scales, common sense runs out. The paradoxes are maps of exactly where common sense meets its limits. This is also why the mathematical and scientific training that lets people engage seriously with these paradoxes is valuable, not as a replacement for common sense, but as an extension of it into regions where common sense alone cannot reach. The calculus that resolves Zeno's paradox is not common sense. It is the formalization and extension of patterns of reasoning that common sense begins to feel for but cannot complete. The axiomatic set theory that resolves Russell's paradox is not common sense. It is the careful, systematic reconstruction of intuitions about collections and membership that had been implicit and therefore vulnerable. Education in mathematics, logic, and science is, among other things, education in how to extend common sense into unfamiliar territory without losing touch with reality. The paradoxes we have explored are exemplary cases of this extension. They are also warnings. Even after the extension, there are further limits waiting to be discovered, further paradoxes that will again require revision and rebuilding. No one who has thought seriously about these paradoxes comes away believing that all the important questions have been answered. The opposite. Engaging deeply with them reveals how many important questions remain open, and how much work there is still to do. The liar paradox, first noticed by ancient thinkers, is still actively debated in the philosophy of language and formal semantics. The unexpected hanging paradox is still discussed in epistemology and game theory. The Barber and Russell's paradox are settled at one level, but the deeper questions they raised about the foundations of mathematics are still being refined. Zeno's paradoxes are resolved mathematically, but physically they point toward questions about the structure of space-time that we cannot yet answer. The grandfather paradox is unresolved in a fundamental way. We do not know whether the laws of physics permit or prohibit the physical conditions it describes. These are not failures of human inquiry. They are its ongoing achievements. The most important advances in understanding have come not from answering questions definitively and moving on, but from understanding questions more deeply, realizing that what looked like a single question was actually several and that answering one part revealed new questions underneath. The paradoxes have served, and continue to serve, as engines of this process. They compress an enormous amount of conceptual difficulty into a compact, vivid form. They make the difficulty undeniable, and they motivate the search for better understanding with an urgency that more abstract discussions often lack. A student who genuinely grapples with the liar paradox not just reads about it, but really tries to resolve it and finds that every apparent resolution leads to a new problem, comes away with a visceral sense of what it means for a formal system to have genuine limitations. That sense is worth more than any number of lectures on the topic. A student who grapples with Zeno's paradoxes and works through the mathematical resolution using limits comes away understanding the calculus at a deeper level than a student who simply learns the techniques. The paradox motivates the theory by showing what problem the theory solves. A student who thinks carefully about the grandfather paradox comes away with genuine questions about the nature of time, causality, and physical law that motivate further study in physics and philosophy. The paradox is a doorway into some of the deepest questions in science. This is the pedagogical value of paradoxes, beyond their historical and technical significance. They create a need for understanding that makes the subsequent learning genuinely meaningful. They demonstrate that thinking carefully about familiar things leads to surprising discoveries, and that the world, at its foundations, is stranger and more interesting than everyday experience suggests. The willingness to take paradoxes seriously, to follow the logic wherever it leads, even when it leads somewhere uncomfortable, and to rebuild understanding when the existing framework proves inadequate, is one of the defining characteristics of scientific and mathematical progress. The history of these particular paradoxes is a history of exactly that willingness, expressed by some of the most penetrating minds across more than 2,000 years. That history continues today, in the laboratories, offices, and seminar rooms where physicists work on quantum gravity, where logicians refine formal systems, where computer scientists probe the limits of computation, and where philosophers examine the concepts of truth, knowledge, causality, and time. The paradoxes are not solved and shelved. They are living questions, still doing the work of pushing understanding forward. And that is why understanding them, or rather, understanding why they resist understanding, is one of the most rewarding intellectual journeys a person can take.